exercise problem is consider an infinite slab of charge with thickness 2a. Shown in this picture, it's centered in the y-x plane. The charge density depends on where we are vertically. And let's try and find the electric field outside this block of charge. So let's start off with a picture. I'm going to try and draw 2D and 3D. So in 3 dimensions, this is a block of charge or a slab of charge. Looks something like this. And if we were to draw a 2-dimensional cross section, it would look something like this in 2 dimensions. So the z-axis goes right through the center. So let's see if we can get that z-axis on there. Right smack through the center. So it's centered about z equals 0. And that also goes through the center here. There's z equals 0. And the thickness of the plane is 2a, so on the top we have z equals plus a, on the bottom we have z equals minus a. So that's what we have. It's a 3D slab. We'll try and work with the 2D drawing just because it's easier to draw. The charge density is thickest in the center and it goes to 0 at the edges, and we know that because of the expression for the charge density. So we're going to try and find the electric field, which means we're going to want to use Gauss's law. Let's write down what Gauss's law is. So Gauss's law says that the net electric flux equals the integral of E dot dA equals the amount of charge within a closed Gaussian surface divided by epsilon naught. So there's our Gauss's law expression. So since our Gauss's law deals with a closed Gaussian surface, let's identify the closed Gaussian surface in our picture. We're trying to find the electric field somewhere above the plane. So let's pick a Gaussian surface that's partly inside the plane and partly outside. I'm going to draw the 2D one first, and then I'll add on the 3D one afterwards. So an edge-on view of our Gaussian surface would be in the plane and out of the plane. So there's a picture of what our Gaussian surface looks like edge-on. I'll give it a shot in 3 dimensions. So sticks up from the top. And then cuts all the way through, down through, to come out through the bottom. Something like this. I'm not super at the 3D drawing, but hopefully you get the idea. So there's our closed Gaussian surface. The area of the cross section is A. So this part right here has area A. It has a height relative to the z-axis of plus z on the top, so it goes up to plus z here, and it goes down to minus z here. My drawing is not 100% perfect, but just imagine it's symmetric on both sides. So it goes up to plus z here and minus z here. Did a little better on the 2D drawing. So there's our Gaussian surface. Cross-section area equals A. The volume would be the area times the thickness. So area times 2z is the total volume of that Gaussian surface. And let's see how we're going to start to apply Gauss's law. So to start, Gauss's law says the net electric flux through the Gaussian surface is E dot dA. So we have 3 places where we're going to get flux: through the top of the box, through the sides of the box, and through the bottom of the box. So let's see how we're going to calculate our net electric flux. Let's fill our electric field in there first. So the electric field comes straight out of the plane. Something like this. So there's our electric field vectors. And we have the same thing on our 3D picture. So there's our electric field vectors. Did it in the yellow so we wouldn't cover up all the other things. So let's say that our net electric flux will be the flux through the top, plus the flux through the bottom, plus the flux through each of the four sides. Let's do the sides first. So the net electric flux through the sides is the integral of E dotted with dA equals the integral, since E dot dA is a scalar product, it's the same as the magnitude of E times the magnitude of dA times the cosine of the angle between them. So if we look at our picture, every little area element on the sides sticks straight out from the sides. There's dA for that side, here's dA for the front, dA for the back, or for the left side, and dA for the back. Okay, that's in my 3D drawing. On my 2D drawing, I can only draw these two sides. There's dA, there's dA. A little bit of the area on the surface of that Gaussian surface. Easier to see on the 2D picture that the area, the dA, the element of area, is perpendicular to our electric field, so the angle between them is 90 degrees. Cosine of 90 is 0, so our net electric flux through the sides is 0. That makes sense because electric flux is how many electric field lines cut through an area. None of these field lines cut through the sides, so the flux is 0. So let's do the net electric flux through the top face next. That equals the integral of E dot dA, which is the integral of E times dA times the cosine of the angle between those two guys. On the top face, a little area element looks like this, points out of the top face straight up. Those two guys are parallel. So the angle between those two guys is 0. If we're a constant distance away from the slab, then our electric field is going to be a constant value. So E comes out front. The integral of dA is A, so our flux through the top is E times A, remembering that A is the cross-sectional area of that Gaussian surface. Okay, so that deals with the net electric flux through the top face. What about the flux through the bottom face? That's the integral of E dot dA, which is the integral of E times dA times the cosine of the angle between them. Let's go back to our picture. The bottom face, the area element sticks straight out. On our 2D picture, we see it comes straight down like that. Again, the area element and the electric field are parallel, so the angle between those two guys is 0. So then what we see is we get the same result that we had for the top face, that the flux through the bottom face is E times A, where A is the cross-sectional area of the Gaussian surface, so the area of the top face of that block that we picked. So our net electric flux is going to be 0 plus E times A plus E times A. Equals 2 times E times A. There's our net electric flux through the Gaussian surface, which we chose as a box that partly sticks out on the top and bottom that's symmetric around both sides. For the next part of our Gauss's law, we have to figure out how much charge is inside this Gaussian surface. So we'll go on to a fresh video and we'll find that amount of charge in the next part.